Welcome everyone. My name is Dale Hegland and I am the Director for North Dakota LTAP's program, a program of the Upper Great Plains Transportation Institute at NDSU. Today's presentation is hosted by the Transportation Learning Network, a program managed by the Upper Great Plains Transportation Institute at North Dakota State University. The Transportation Learning Network is a partnership of Montana DOT, North Dakota DOT, South Dakota DOT, Wyoming DOT, North Dakota LTAP, and the Mountain Plains Consortium. The consortium includes Colorado State University, North Dakota State University, South Dakota State University, University of Utah, University of Wyoming, Utah State University, University of Colorado Denver, and the University of Denver. During today's presentation, please jump in and ask questions by typing them into your chat box at the bottom of the webinar window. You'll be in the listen-only mode, with your computer speakers providing the presentation audio. This session will be recorded. Should you want to review the presentation anytime in the future, as a TLN member, you can go to the LMS system. If you're not a TLN member, we'll post the contact info in the chat box as a means for you to secure a link to the recording and presentation handout at a later date. Today's technology transfer will hand off findings from a Mountain Plains Consortium research project completed by the University of Wyoming. We have 102 registered for the webinar. The webinar will last 1 hour, and we have interest from across the entire U.S. and around the globe. Our topic is implementation of intelligent compaction technologies for road construction. Our speaker, Dr. Kam Ng, is an assistant professor at the University of Wyoming, College of Engineering and Applied Sciences. Kam received his PhD in civil engineering from Iowa State University and is also a professional engineer. His background includes field engineer, consultant, contractor, researcher, and instructor. Kam's research background covers a broad spectrum of foundation engineering and material interaction areas. His most notable research awards are from the Deep Foundation Institute and TRB. Dr. Kam, I'll now turn the webinar over to you to begin presenting on your research. And thank you for joining us.
Thank you, Dale, for the kind introductions. And before I begin the webinar, I'd like to acknowledge the financial support from the Mountain Plains Consortium to make this research successful, and also like to acknowledge the contribution from the Wyoming Department of Transportation, and also I'd like to acknowledge my colleague, Dr. Khalid Sabadi, a professor in transportation, and my former graduate students, Christopher Savon, that contribute to this research. A very brief outline of the webinar presentation by begin with a very brief introductions of the intelligent compaction and a very brief background of the intelligent compactions. What I want to do, focus is to present and share some of the outcomes of the recent surveys, and to present the framework of the economic analysis of the intelligent compactions, and finish up with conclusions and recommendations. To facilitate the implementation of intelligent compaction and to achieve the long-term goal of improving the pavement quality and road safety and reduce construction costs and durations, we will try to focus on 3 objectives in this research. To examine the current intelligent compaction IC technologies and practices, evaluate intelligent compaction implementation across the states, and most important is to develop a framework for the economic analysis of the implementations of intelligent compaction. A very brief background: current road compaction methods are highly operator dependent. Just some of the limitations of what we have with the current road compaction methods and procedures. Second limitations could be The roller passes are often inconsistent, and as many of you know that the current road compaction's quality control and assurance was performed using a point load test method. The coverage of the quality control and assurance are minimal. I would say less than 1% of the roadway section. So what exactly is the intelligent compaction? In order to have an intelligent compaction, the compactor roller must be equipped or installed with the following features and sensors. Most important is a accelerometer that measures the soil stiffness as the roller is compacting and roll over a road section, and also at the same time we must have a controller that to adjust the compaction vibration. We must have the data to be displayed using the LCD display, and to locate the measurements at the specific location. We'll use the GPS system with the GNSS antenna to collect the GPS information and overlap with the measurement collected by the accelerometers, and those information will be displayed, and also that the roller could be installed with angle sensors to measure the rotations and the positions of the roller. So to have those features and sensors installed onto a roller, that will provide three main characteristics of the intelligent compaction. The IC will allow us to perform a continuous assessment of the soil and the pavement stiffness. Roller operation will be automatic adjusted in terms of the vibration amplitude and the frequency, and the integrated GPS will allow us to have a real-time mapping of the stiffness as shown on the figure there, that we were able to cover the entire area to indicate the measurement values as a respective locations. Some of the potential benefits of the intelligent compaction, those are gathered from the literature review of our study. Higher quality compaction, that we believe that IC will provide a higher quality compaction, will improve the construction, and most important is roadway safety, improve the coverage for QA and QC testing, and improve the roller pass consistency, reduce construction and maintenance costs as reported in the literature. And this is the figure to show that what the IC can do with in terms of measurements compared with the current compaction and QA/QC methods, that the IC were able to cover 100% of the compacted sections, whereas the current point load test methods will cover about less than 1% of the quality of the root sections. This is not a technology that's specifically designed by just one company, but many different companies have their own systems, software, and measurement values. Some of the typical companies or vendors that provide this intelligent technology, like Caterpillar, Dynapac, Domac, Sakai, and Case, that just to name a few, and they have their own design display features, screens, and measurements, as also summarized on this slide here. A table shows different vendors, different models, and different software used to collect and process the data. And most important is, you will refer to the column under IC-MV, is the intelligent compaction measurement values. So the measurement values collect and measured during the compactions varies from vendors to vendors. Primary is to measure the stiffness or the modulus of the compacted soil or the pavement material. The details of those and the calculations or derivations of those measurement values has been clearly described or explicitly described in the NCHRP report 676. So I will not get into these details here. This has been studied by many experts and has been summarized in the NCHRP report. In terms of the compacted or influence zones under a compacted roller versus some of the typical point load test methods, there's questions about maximize the button above the slide to show the presentation full screen, and Chris or Dell, would you able to do that?
Each person can do that on their own.
Oh, okay. All right. In terms of the zones or influence depth, the compactor roller using the intelligent compactions can cover a width of 2.1 meter, as for the depth will be from 1 to 1.2 meter, whereas the other point load test, for example the LWD or the FWD, will cover a depth of only 0.3 meter. Other gauges like the nuclear density gauge will cover a depth of 0.3 or 12 inches depth. For the DCP, of course, is a point with no width, and the depth can go as deep as 3 meter. So if you were to use the intelligent compactions and you collect a lot of data onto your onboard computers, how do you compile the data, analyze the data, sort out the data, display the data, and process the data? So definitely you need a data management tool, that a program, what we call a data software, funded by the Minnesota Department of Transportation and developed by TransTech Corporation. I include the link at the bottom here that you can download the software for free, and basically the software allows you to upload and download the data from the onboard computers on the roller down to your computer or personal computer for analysis. With the data, you can generate a map of compaction data or compaction map and perform correlations of the measurement values with the institute test data, and determine sections that meet the QA/QC specifications or the target value, and allow you to better evaluate the performance of the compacted sections using this software. So this is some of the outcomes of our study. Starting from here, that what will be the current compaction specifications, that we will just want to summarize it for, as many of you know, that today we still use some of the very conventional methods to evaluate compactions. For soil and aggregate layers, we will typically use nuclear gauge, proctor densities performed in the lab for reference, sand cone as a reference test method. For pavement, we could have cores for testing, nuclear gauge, non-nuclear gauge, or electric density gauge for measuring and determining the performance of the compacted sections. So what other DOTs has been doing with the implementations of the intelligent compaction is that they will use intelligent compaction as a complement to the current methods. So they still use the current test methods, institute test methods like the DCP, sand cone, nuclear gauge for their QA/QC, whereas the IC will be used as a complement depending what options. There are three main options that you can integrate or incorporate IC to the QA/QC. That is described again, detailed descriptions in the NCHRP 676 report. Actually the authors are from the author by the Michael Mooney and his group, and David White and his group. There are few people that working on that produced that report that clearly describes all these details. Three main options. Option one is you use IC to identify the weakest area, where the area has soft compacted zone, where you will focus on those areas and achieve the target density, and also to perform apply in-situ tests at that location. Option two is to measure how uniform is the compacted sections by comparing means values of the measurement values from over the areas of the compacted section. Option three is we will make use of the intelligent compaction, is to have an calibration sections, shorter or sections for you to calibrate the intelligent compactions to some of the typical in-situ test values, and develop and establish a target measurement values for subsequent actual compactions using intelligent compaction. So that's more extensive in option 3, but you have a choice of 3 options and integrate and incorporate the intelligent compactions to the QA/QC. In terms of IC specifications, FHWA has developed specifications for use by the transportation agencies, and in fact at the time when we conduct the research, was currently being adapted to the AASHTO specifications. I checked that AASHTO has come up with the specifications, which you can go to the website to purchase the AASHTO specifications on the intelligent compaction. As for the study, in 2014, 18 states are in the process of drafting or adopting IC specifications. I believe today there were more than 18 states. At that time, more than 30 states have conducted the workshops or demonstration projects for IC. I believe today there were more states than 30 states. This is the US map that's summarizing states that have drafted or in the process of drafting the IC specifications for pavement and soil. The one with the solid shaded, those are the states with both pavement and soil specifications using IC. And some states have developed IC for soil, and some states have developed IC specification for pavement. So we'll get into the research outcomes. First, I'd like to share with you the outcomes of the Wyoming survey, that we have total 79 respondents that participate in the Wyoming survey. We give them a list of questions and answer options for them to choose, and I want to bring up this particular questions is, do you have any concerns with IC or IC implementations? And the following answer options are cost, reliability of the data, reliability and durability of the technology, not a specified quality control assurance method, lack of operator ability and or time and cost to train operators, unfamiliar with the technology, there are no concerns, or others. So the response, out of the 79, 72 people answer these questions. I highlight the first row is cost. Cost has 24 people select this option, that 24 out of 72 participants have a concern about the cost associated with the intelligent compaction. That will have a percent of 33.3%. That's the highest concern among other options. The next one is the reliability of the data. 19 respondents selected this as one of their concerns, and in fact they can choose as many options they would like. as long as they think that those are their concerns. So based on this outcomes, we understand that the Wyoming community are concerned about the cost of implementing the intelligent compaction, and they're also concerned about the reliability of the data. We also sent out a nationwide survey, and total of 32 respondents from 32 states participate in this survey. Those states participate are shaded on the map here. And I would just like to share some of the outcomes of the nationwide surveys here. And this particular outcome is to understand the DOT knowledge and the use of intelligent compaction. The question was, which aspects of the intelligent compaction is your agency familiar with? Select all the options that are applicable. If you look at the highest percentage, 90%, in other words 27 out of 30 participants select that they are familiar with the technology used during intelligent compaction. 90% they're familiar with this technology. The next lowest percent is 76.7%. Again, they are 23 participants are familiar with the operation of the intelligent compaction rollers. Continue with that, 56.7%, that 17 participants are familiar with the quality control and assurance standards. The least percentage, or the lowest percentage, is 50% here, that 15 out of 30 participants are familiar with the costs and benefits. So I want to highlight here is that they are least familiar with the costs and the benefit associated with the use of intelligent compaction, especially the cost. Another question is to understand the DOT concerns about using intelligent compaction. Again, the question was, does your agency have any concerns with the use of intelligent compaction for soil or pavement materials? Answer options are: there are no concern, cost, reliability of the data, ability to have it approved as a quality assurance technique by the policymakers, least strict than the current quality assurance methods, lack of staff knowledge to confirm the data. So you can see the widespread in terms of the answers here. 29 participants, and the highest concern I can see from these numbers here is 41.4%, which is the ability to have it approved as a quality assurance technique by the policymakers, and the lack of staff knowledge to confirm the data. So these are the two highest percentage that reflect the major concerns by using intelligent compaction, followed by reliability of the data, the cost. Those are the several other concerns that using intelligent compaction by the DOTs. In terms of the IC QA/QC specifications, the question was, has your agency ever drafted quality control or quality assurance standards for intelligent compactions? We have answers for yes and no, and also among the three yes, we have different details in terms of the answers. Quality assurance standard for IC have been adopted, or the draft standards has been completed or waiting adoptions. We are in the process of drafting the standards. We have two options for no. No, but we plan on drafting the standard. No, we do not plan on drafting the standard at the current time. So if you look at the higher percentage of the response, 38.1% say that no, they do not draft the IC QA/QC specification, and they do not plan on drafting it at this current time. So I'm sure they have concern about using the IC at the current time, and that is the limitations and the obstacles of the implementations of the intelligent compaction. But if you add up all the participants that answer yes, we have 3, 4, and 5, total of 12 people say yes, but either in the process of drafting, adoption, or implementing the QA/QC specifications. We also want to understand the cost associated with the intelligent compaction. Either they have those information or what they believe about the cost that will whether increase or decrease with the implementation of intelligent compaction. You can see there are two main groups there. The first group that believe, 31%, or 10 out of 32 believe that the cost will increase. The other groups say that they're not sure whether the cost will increase or decrease with the implementation of intelligent compaction. So from this outcome of the survey or questions, that we understand that more than 1/3 they have no information or knowledge about the cost, and then 1/3 of the people say that they believe, or either they have information that the cost will increase. Particularly regarding the cost associated with intelligent compaction, only 3 respondents mentioned that information related to the long-term cost. So they have information on the long-term cost, and in particularly one respondent from Texas indicate that the long-term period yield higher benefits than the cost. So that's good news for the full implementations of the intelligent compaction, so that we need to look at not only the initial cost but look at the long-term cost to be considered in our economic analysis. So based on the outcomes of the survey, we understand that there are people concerned about the cost, and people have no information about the cost, and we think that this is one of the major factors that will hinder the implementations or the adaptations of intelligent compactions. And we searched through literature and we found limited study or no study on the benefits and costs associated with the implementation of intelligent compactions, and we felt that this is an important topic to address. So we one of the focus or objectives is to develop a framework for economic analysis of intelligent compaction, so that transportation agencies can use this as their basis or foundations for future investigations about the costs associated with intelligent compactions. The framework addressed 2 main components, construction cycle and cost, and also the roadway life cycle. To present the framework and facilitate the presentations of the framework of the economic analysis, we presented 2 case examples to show how we'll use this framework to calculate the costs and the benefits. We present 2 case examples, 1 pavement overlay, and case study example 2 new road construction. Before I get into the framework and the examples, I like to define some of the terminologies or equations that we use in the calculations. Construction cycle is defined as the time period begins with the preparation for roadway construction or compaction. So this is our definition for construction cycle. Construction cost, we have an equation to determine the construction cost as equation 5.1 given listed in the report. basically is the compaction time in hours. How much time for compaction in hours multiplied to the cost of the roller per hour plus the operator cost per hour and also the GPS cost per hour considering using the IC technology, and finally add or plus the QA/QC cost per area multiplied to the total area. At least this is the basic equations that we think this will pretty much applicable to everybody, because you will definitely have costs on the roller, operator, GPS, and the QA/QC. So that's how we define the construction cost. In terms of the hours needed using the intelligent compactions, we have a definition for IC hours. IC hours is equal to the conventional compaction hours for roadway section. In other words, the amount of hours that to complete the roadway compaction using the conventional compaction method plus the conventional compaction hours for the test section. So in the IC you will have a test section to calibrate or to establish a target value, so we need to consider that time performing the test section. That whole thing, parenthesis, multiplied to 100% minus IC efficiencies. That will give us the intelligent compaction hours needed to complete the same 1 lane mile road sections. Cost per, actually it's not lane but line item, cost per line item. So we have costs associated with roller, operator, and many other items. So cost per line item is equal to hourly rate of the line item cost multiplied to the calculated hours. Either it's the conventional compaction hours or the IC compaction hours. The last one is the QA/QC cost. What will be the cost required to perform the QA/QC? Hours to perform QA/QC multiplied to the area of the QA/QC per hour multiplied to the cost of the QA/QC per areas. Eventually you will get the amount of cost to perform the QA/QC for that specific area. So that will able us to present it in a simple framework to show you how you will go through the process of calculating the cost. We have the flow chart for the conventional compactions, and we have the flow chart to calculate the cost for intelligent compaction. So first, for the conventional compactions, we need to know the number of hours to compact 1 lane mile. So in this example, we always use 1 lane mile as the unit section. So the number of hours for the conventional compactions to achieve the compactions of 1 lane mile road, and then we have the hours, we multiply to the line item unit cost to give us the total cost, and then plus the cost associated with QA and QC, that will give us the total cost required for conventional compaction. To calculate the number of hours required by the intelligent compaction for the same 1 lane mile, then we need to use the equations 5.2, which is, let me go back here, equation 5.2 basically is the IC hours here. So the IC hours is the amount of hours required by the conventional compactions multiplied to 100% minus IC efficiencies. So that's how we get to an equivalent number of hours required by the intelligent compactions. Again, once we have the number of hours, we multiply to the cost for each line item, and we add the cost of the QA/QC. That will give us the total cost required by the intelligent compaction. So that's the flow chart that describes how we're able to determine the construction costs for both conventional and intelligent compactions. In terms of the roadway life cycle, so we need to also consider what would be the benefit, or in terms of cost, based on the life cycle, the service life of a road. So we believe that IC provides a more uniform compaction and will extend the pavement life. So the cost per lane mile per year is the unit used for comparison. So the cost per lane mile per year is equal to the cost of the roadway per lane mile divided by the service life in years. So we begin with the example number 1. Is a 2-inch thick asphalt pavement overlay, a single lane mile with a 500-foot IC calibration section. We gather one of the challenges was to gather cost data so that we can perform the cost analysis for these examples. We gather the cost data from companies, contractors, from Wyoming DOT, from the equipment manufacturers and rental companies, and from literature that allow us to have enough cost data to perform the task. Another challenge is to determine what will be the IC roller efficiency. We're able to file this document by Brett and Sewell from Texas A&M that they conclude that the IC roller efficiencies will be 30%. The roadway life cycle compared with the roadway life cycle using intelligent compactions will increase by a factors of 2.6 compared to the roadway life cycle compacted using a conventional method. So from Chan 2012 we're able to get this number to show that the life cycle of a road compacted or accomplished using intelligent compaction will increase by a factors of 2.6. With all this information and the cost data that I summarized on the table here, that although it may not be very clear, but I just will briefly go through here that I show you the item, the unit cost or the unit parameter, and where we get the information from. And I'd like to thank all those people that contribute to this research: contractors, Wyoming DOTs, rental companies, manufacturers and vendors that listed here. Specifically, I want to highlight that the conventional roller cost for compacting a pavement layer per hour is $36. That's the number we come up with. The IC pavement roller cost or rental cost per month is $7,500. Roller operator per hour we estimated to be $30 per hour. That's the cost of an operator. The amount of hours for performing the conventional compactions per lane mile is 10 hours. Compaction cost per square yard is 20 cents, and GPS rental per year is $1,800. And we assume of a test sections of 500 feet, and we also assume that we have 40 working hours per week. That will be the required cost data for construction cost estimations. In terms of the life cycle costs, we know that the road life cycle accomplished using IC will increase by a factor of 2.6, and we assume of a typical asphalt life cycle is 10 years accomplished using a conventional method, 10 years lives. And the cost per lane mile that we gather is about $250,000 per lane mile. That is a total cost to have a 2-inch thick asphalt overlay for 1 mile long road. So using all this cost data and the definitions that I described early, that we come up with this table here to compare what would be the construction cost for conventional compaction versus the construction cost using intelligent compaction. So let me use a pointer here. So let me begin with the roller here. So the roller under the conventional compactions, the roller cost per hour is $36, and we need 10 hours to accomplish the 1 lane mile compactions. So the total cost for using the roller is $360. For the operator, we gather $30 required to pay the operator per hour, and we need 10 hours to accomplish the 1 lane mile compactions. So the total cost for the operator is $300. We will not use the GPS because this is a conventional compactions. For the QA/QC, we have an equivalent unit cost here, 4 cents per square yard. For a 1 mile lane road with a width of 12 feet, we calculate the area of the road as 7,040 square yard. We multiply this area to the unit cost, 4 cents, and we get the associate cost for QA/QC as $281.60 cents. Then we add all these costs for roller, operator, and QA/QC. We end up with $941.60 using the conventional compaction to compact 1 lane mile road sections. For the intelligent compactions, again, we'll need to determine the number of hours, an equivalent number of hours, to accomplish that compaction of 1 lane mile road. So the numbers of hours here is 77.7. 7.7 was determined by considering 1 mile road sections, plus in the intelligent compactions we have a 500 foot of the test section, so that is equivalent to 0.1 mile. So the total road sections that required under the intelligent compaction is 1.1 mile. So we take 1.1 mile, multiply to 10 hours required by conventional compactions, and then multiply to 100% minus the IC efficiency, which is assumed as 30%. So this is how we end up with the number of hours, 7.7. Basically 1.1 mile multiplied to 10 hours multiplied to 70% to give us 7.7. That would be the number of hours required to accomplish the job using intelligent compactions. The roller cost. The roller cost, we gather the information of $7,500 rental cost of the roller per month. We divide the number of hours per month. We get $42.61 of the roller per hour. With this unit cost, we multiply to 7.7, and we get the total cost for the roller as $328.10. So I think that's one question, whether it's scheduled to start at 10 Central Time. I think the answer is yes. Let me continue with this explanation here. For the operator, we assume that we'll pay the same rate to the operator, whether it's using a conventional compactor roller or intelligent compaction roller. So the unit rate is still $30, but then the number of hours is less now, 7.7 hours. So the amount of cost for the operator is $231. In the intelligent compaction, we require to use the GPS, assuming that you will not have that, or you need to rent a GPS, which is about $1,800 per year and equivalent to about 89 cents per hour. So the 89 cents multiplied to 7.7 hours, that will be the cost associated to compact required for 1 lane mile plus the 500 feet test section as $6.85. QA/QC, if we were to use intelligent compaction, the QA/QC in terms of performing point load tests like the Nuclear gauge, sand cone, or those deep conventional test method is required only on the 500-foot test section. So once you have performed the point load test on the 500-foot test section, we're able to establish the correlations or the target value and apply those informations for the actual 1 lane mile compactions. So the QA/QC only applicable to that 500 feet sections using the intelligent compaction. So the rate is still the same, but then the area is equal to 500 feet multiplied to the width of the test section, 12 feet, that gives us an equivalent 667 square yard. So that multiplied to the unit cost gives us the QA/QC cost as $26.68 for the QA/QC. So you add up all the costs here, the roller cost, operator cost, GPS, and the QA/QC. The total cost required for intelligent compaction is $592.63 cents. So this is what we come up with based on the our definitions and the cost data that we gather, and we learned that the intelligent compaction were able to reduce the cost by about 37% based on this study. In terms of the roadway life cycle, right, we have a conventional road compacted by conventional compaction method, that an asphalt road will last for 10 years. That's our assumption. The cost per year, because we gather the cost of 2-inch thick, so there's one question that is the cost per unit of IC for an hour given in the table. Yes, the cost of the IC, let me bring it back to the previous few slides here. So the cost given here, so that we able to gather the cost of the IC roller per month, which is $7,500, and we divide that with the number of hours per month. That gives us the unit cost for the intelligent compaction roller. That's how we get to the cost. Let me continue with this. In terms of the roadway life cycle, we gathered information from YDOT and other agencies that we estimated about $250,000 for overlaying 2-inch thick asphalt pavement. So we take the $250,000 divided by the service life of the road, we end up with $25,000 per year. That's how we calculate the cost per year associated for a 10 years life cycle. If we will use intelligent compactions from the Chen 2012 documents, that they believe the service life will increase by a factors of 2.6. So we take 2.6 multiplied to the 10 years of the conventional method. We believe that the service life will extend to 26 years if the road will be compacted by intelligent compaction. So this is how we get 26 years here for the roadway life cycle. Again, the cost per year will take $250,000 divided by 26. That's how we get the cost per year. So if you were to compare the cost per year here, obviously we can say that we will save about $15,000 per year in terms of benefit or saving using the intelligent compactions. Then people may argue that, what if 2.6 factors or 26 years is not realistic, maybe it will last shorter than that, or how about the roller cost will be different from places to places? What if the efficiency of the intelligent compaction is not 30% but other values? In the study we did some what we call the sensitivity studies. A question pop up here is, do you repeat the test section for QA/QC, or is the 500-foot initial test section used for the entire project? The in this exercise here, we assume that the 500-foot initial test sections will be used to establish the required target value or correlations for us to be used for the entire project 1 lane mile. So that actual compaction of the 1 lane mile will only evaluate using the intelligent compaction measurement values. So is there any additional QA/QC test on the roadway other than the 500 test sections? In this example, we did not include the QA/QC on the other road sections other than the 500-foot test sections. But if this is not the practice, obviously you can modify this framework here to include the QA/QC for the other road sections that other than the 500-foot test sections. So based on this study, example number 1 with 2-inch thick overlay pavement, we have a saving about $15,000 per year, but then people may argue that there's some uncertainties in terms of the numbers, the IC efficiencies, the extended life cycle. So we did some sensitivity studies or the parametric studies to look into a range of values. For example, what I'm going to show you is that a range of intelligent compaction efficiencies varies from -15% to 45% on the x-axis. So let me switch off the pointer here. So on this graph, what I'm showing is that what if my IC efficiency is not 30%? What is some other values? So we'll cover a range from -15% to 45%. And then we go through the same exercise. For different IC efficiencies, we determine the cost difference of the conventional to IC. So going through the same calculations here and plot the data on this graph here, we saw that the IC efficiency will break even when the IC roller efficiency is -13.7%. So in other words, if you don't have an efficiency gain using the intelligent compactions, we believe that you still have some saving using the intelligent compaction, primarily from the QA/QC sections. Because if we assume that if you do only tests on the 500-foot test section using the point load test for establishing the target values or correlations for the entire roadway, then that is the saving you have using the intelligent compactions. So even if you don't gain any efficiencies in terms of hours, that using intelligent compactions you will have a cost saving here based on this study here. The report also includes other sensitivity study on roller compaction rate, on different extended life cycles, on other parameters that we believe will change from places to places. Now we get into the example number 2, where we will have a single lane mile new construction. We have 5 layers here. We have subgrade, subbase, base, vital, surface. We have 500-foot IC calibration sections, and again we'll use a 30% IC efficiency here. So this is the cost data that again we gather from different companies, and we want to highlight is that we have the conventional road roller cost per hour $34.03, and we have the pavement roller at $36 per hour, and then the IC soil roller costs $7,000 per month, whereas the IC pavement roller costs $7,500 per month, and the rest should be pretty much the same. So this is the outcome of the study in terms of the cost comparison between conventional and the intelligent compactions. Now we have soil and pavement, so we calculate the soil layers and we calculate the pavement layers. in terms of the roller cost, and we end up with this cost here for the soil roller. Let me use a pointer here. So this is the cost for the soil roller, and this is the cost for the pavement roller, and this is the total number of hours required to compact all 5 layers. We have 3 soil layers and 2 pavement layers, and the total cost for conventional compaction is $2,704.41. Whereas for the intelligent compactions, again, we will calculate the equivalent intelligent compaction hours, and we end up with $1,234.08. That is our cost using the intelligent compactions. And then based on this new road construction, we see more saving. That's about 54% saving in terms of the construction cost. So a few more slides to wrap up this webinar here. Conclusions that we believe the IC improves the roadway quality and decreases the roadway related costs. IC provides 100% coverage of the compaction. Most Wyoming professionals are supportive of the implementations of IC, but they're concerned about the cost and the reliability of the data. 1/3 of the National Survey respondents indicate that the construction costs using IC will increase. Another 1/3, they are not very sure about the cost and the benefit. IC, when used efficiently, can produce a 37% decrease in the construction costs for the overlay, or about 54% for roadway construction based on this study. Improved pavement performance will extend the pavement service life, and that will have a cost saving of about $15,000 per lane mile per year in cost saving. In terms of recommendations, if your states have not a demo project, that maybe you should consider working with the FHWA to secure funding for one or few IC demo projects. Adopting IC QA/QC specifications during the demo project as a special provision. Analyze the QA/QC data from the demo project to evaluate the performance of IC roller. To analyze the cost data, that is important, to account for both training expenses, anticipate IC courses during the training of the people. Begin a monitoring program of the pavement sections that the demo project took place, so that to monitor how the performance of those roads in terms of the life cycle, that able better predict their costs over the years. Prepare subsequent demo project to confer the results from the first one, and to test sections for the applications of the IC, and maybe draft QA/QC for adaptations by the local or regional agencies to promote the IC, and for contractors to follow, and to facilitate the implementation and improve the roadway construction and cost and safety.
Well, wonderful handoff of technology transfer, and thank you participants for joining. Participants could use your help if you stay online just a second and fill out the evaluation. That'll automatically pop up. We do want your feedback. That concludes today's presentation. Dr. Kam, thank you. Very informative. Thank you very much. Thank you, everyone.